In this video, we're going to introduce PNP BJTs, which will leverage much of what we learned from NPN BJTs. I've included three of our common representations of NPN BJTs on the left of this slide. I've left out the full Ebers-Moll equations, but both the Ebers-Moll diagram and the IV curve are standing in for them. We're going to slowly introduce PNP representations on this page and compare them against the NPN representations. The first thing to look at is the PNP schematic and the terminal assignments on it. You can see that they're upside down compared to an NPN BJT. I've labeled the topmost connection on here the emitter, with an arrow running from the emitter to a base indicating a diode that points in towards the base instead of out towards the emitter. And I've drawn the collector at the bottom. The currents have switched directions, so current flows into the emitter and out of the collector and the base. And the base emitter and collector emitter voltages are now upside down as well. So they're positive, increasingly positive as the base drops below the emitter and as the collector drops below the emitter. We picked this arrangement because the PNP transistor is turned on by lowering the base voltage below the emitter voltage. And that's consistent with what we know of the construction of PNPs. The PN junctions inside PNPs are reversed relative to NPNs, so you'd want the P emitter higher than the N base in order to forward bias the base emitter junction. You can see that clearly in the PNP version of our Ebers-Moll model. The diodes have switched direction here because the base has to be below the collector or emitter to forward bias the PN junction between the base or the emitter. And so that means that almost all the logic we applied making the NPN Ebers-Moll model has flipped around too. So the dependent current sources are now pointing out instead of in. And in forward active, that means the collector will sink most of the current passing through the forward diode, such that the base needs to sink very little. So you get a bunch of current here, a little of it goes out the base, and the rest of it goes through alpha F IF to the collector. Which is the opposite of the NPN transistor, where the base needs to source a tiny bit of the current, of the large emitter current through IF, while the lion's share of it is sourced through the collector. It's also worth noting that the emitter in a PNP emits holes, so current flows in the same way as carriers in a PNP device, and that's nice. So there's a large injection of holes from the emitter to the base here. However, even though our Ebers-Moll model is backwards, the wacky redefinition of terminals that we did up here has a magical effect when we go to draw our IV curves. The relationship between IC and VCE is the same in a PNP transistor as in an NPN, but we just need to remember that the emitter is at a high voltage and the collector is at a lower voltage when VCE is high. So this over here corresponds to high E and small c, while this over here usually corresponds to high C and small e. Similarly, these high VBE curves correspond to bases that are significantly below the emitter. So the upshot here is we get to use the exact same IC-VCE plot because we have switched the direction of many of our terminal definitions. Though it's worth noting that early voltages and betas are quite different in PNPs and NPNs, so there'll be some changes in parameters here. Having the same IV curve for the NPN and the PNP means that the underlying model is the same, so taking derivatives of it yields the same behavior. That in turn means that the PNP small signal model is identical to the NPN small signal model. So we can see that there's an R pi between the base and the emitter, and you calculate that the same way. You'd find the value of R pi as beta times phi th over IC. There's a dependent current source between the emitter and the collector. And I flipped the direction on it here. And its value would be equal to GM times VBE, where GM is equal to IC over phi TH. And finally, there's an RO that's equal to VA over IC between the emitter and the collector, representing base width modulation. So the only difference we have to remember with the PNP small signal model is that the emitter is usually attached to a high voltage, unlike the NPN where the emitter is usually attached to a low voltage. However, because voltage sources in a small signal model are shorted, you'll often see the emitters of NPNs and PNPs shorted together if this is attached to the supply and this is attached to ground. So to summarize, because we did some footwork with our terminals, the PNP has the same IV curve as the NPN, which means that the small signal model is the same as the NPN. I'm going to run through a quick example of a PNP in a circuit. This is great practice, so feel free to pause the video and work through the problem by yourself before continuing and watching my version of the answer. We start answering the questions up here by finding the base voltage, which is going to be one diode drop below the supply voltage here, so VCC minus VBE on, meaning the base voltage is 9.3 volts. The supply is still called VCC because of the tradition that is associated with NPN transistors. So you still use VCC even though we attach PNP emitters to it. Once we know the base voltage, we can find the voltage difference across the base resistor and calculate the current through it. In this case, this is 9.3. There's 8.3 volts on this side. So that's 1 volt over 100 kilo ohms is 10 microamps. Since we're in forward active, we know that IC, current flowing down this way, is equal to beta times IB, and 50 times 10 microamps is 500 microamps. And this is pretty characteristic of PNP resistors. Their betas tend to be half or lower than NPN transistors. The maximum collector voltage we can have before the transistor becomes saturated is 9.8 volts. Because if the collector climbs above that, then we won't have VCE sat between the collector and the emitter. And we know the collector voltage is just IC times RC, so we can find the maximum RC as 19.6 kilo ohms. So in summary, PNPs have the emitter at a high voltage and collector at low voltage. The large signal model of the PNP reverses the diodes and current sources compared to the large signal model of the NPN. However, reversing both the terminal definitions and the large signal model means that the IV curve and small signal models for the PNP are the same as the NPN.